Yes, our day had. You can unmute and pray. Kindly unmute and pray. You raised up your hand. But why would someone who is not ready to pray for us raise up their hand? That's indiscipline. That's indiscipline. Yes, Daniela Pretty, pray for us.
Good afternoon, everyone. Let's humble ourselves and pray. Loving Father, we thank you for this day. We thank you for everything you've done for us. Loving Father, as we are going to study today about our kinds, we pray that you may give us the knowledge and understanding to apply whatever knowledge we acquire, and we may not forget it. Give our teacher energy to teach us and also enable us to understand. In Jesus' mighty name I've prayed. Amen.
Okay, so those who attended with us the previous lesson on alkynes, as you can see, this is lesson 2. To begin with, of course, an introduction. Thank you, Daniela Pretty, for the prayer. So we are going to have the introduction. We had the introduction, sorry, where we looked at the definition. We literally looked at all this. Hope you've read through. Under the introduction, we looked at the definition, functional group, general formula, nomenclature, and isomerism. You people went with the occurrency and sources as the take-home assignment. You were briefed how you can make a write-up about the physical properties. The bonding and structure was talked about. You were advised to use internet for that. And today, we are going to look at only and only part E. Why? You all know concern concerning the identity of the triple bond, we have the video already. The video is present on the drive. Towards the end of the lesson, after we have covered E, I'll tell you the location of the video on the drive. And then you all know I never teach applications because they are too obvious. Someone can literally make simple research and they get them at hand. Now, what we are going to handle has a very special note. So for today, we are basically handling reactivity and reaction mechanisms for the what? For the alkynes. And they are saying NB, the addition reactions of alkynes are similar to those, or of alkenes are similar to those of alkynes. So that means if you had issues with the previous lesson 2 of alkenes, you're not going to get this lesson at all, and I'm not going to over explain because most of the things we are talked about the other side. So the reactions are going to be the same. Someone may be like, what are those reactions exactly? So the reactions I'm talking about here are these reactions. I don't know, but we may start having morning lessons starting as early as 10. I don't know why, but the environment is cool and good for classes. Okay. The addition reactions remain. They are these ones. Adding hydrogen, adding the hydrogen halides, adding the halogens, and adding acidified water. They only talked about addition reactions, but maybe we shall also hint something about polymerization. Just something small. They are not very hard. Yeah. Okay. So, we have agreed that today's lesson targets are only 3. The first one, reaction mechanisms. The other one is identity. The last one is applications. So you all know that our triple bond illustrated like that is our functional group. So lesson target 2 is concerning its identity. Then lastly, target 3 is about the application. Agreed, every time they use the word applications, they are trying to show you that we are dealing with daily what? Daily life. Yeah. And you all know you will take this as research. Write that as research. And then you make a report. Then this one, I'll give you the location of the video. So we are going to concentrate on that. Okay. So we officially begin. Of course, chemical reactions. If you missed lesson 12 alkenes, kindly log off and first go and watch that. Otherwise, you're going to just see stars, something I don't really want. So chemical reactions of alkynes, that's what we are handling. So to begin with, of course, we shall begin with hydrogenation. Hydrogenation means adding what? Adding hydrogen. Yeah. And I remember telling people about this thing of adding hydrogen. I think we dealt with this in alkenes. I even tried to show people the fake mechanism. I showed you how you can come up with it without a mechanism, and they are the same things we are going to do. And trust me, conditions are not changing at all, and we are coming up with the same product. So you all know I always give two examples. I always talk of the alkyne, which is straight chain, symmetrical or asymmetrical. I may bring out that which has a branch, such things. And of course, if a branch comes in, it is asymmetrical. That's what I usually use. Then when I teach benzene, we shall always involve aromatic alkenes, aromatic alkanes, aromatic alkynes. That is after I talk about aromaticity. Yeah, it is our second topic after alkyl halides. So you gotta be ready for that. So hydrogenation, or simply adding hydrogen, what happens? So I'm going to begin with our ethane, which is the simplest what? Simplest alkyne, I told you that. So you all are aware that when we add the hydrogen in presence of nickel, I told you the temperature is 100 and what? And 50. I said that and I'm not repeating it. So you all know these ones lead us to alkenes. So you'll be like, how many carbons do I have here? I have two of them. One carbon and two carbons. So even the alkane you're supposed to form should have two carbons. You understand? I'm going to show you the fake mechanism. But literally you need to know that this reagent usually produces alkanes from the alkynes and alkenes. You get? It gets rid of that reagent. You get that? That reagent of hydrogen nick at 150, it always gets rid of that triple bond. Just like we added it to an alkene and we formed an alkane. The same thing is going to happen here. So you all know that one alkane with only 2 carbons is ethane. And that's how it is written. Someone may be like, how come this one had 2 hydrogens and what we are forming has 6? Yet we are only and only adding 2 atoms. Remember, adding hydrogen as H2. So you're adding 2 atoms. But this one had only and only 2 hydrogens. But then the alkane we are forming is having 6 of the hydrogens. That means 4 atoms were added. But according to what we are adding is just H2 with 2 atoms. So someone may be like, where are the 4 coming from? So, and this is where I'm going to best to advise you. So to bring out that, someone may decide to balance. And when someone decides to balance, to bring out the 4 atoms being added, someone may decide to write it as two hydrogens, presence of nickel, still at 100 and what? 50. Get the point. So that person puts a 2 to make sure the calculation comes out. So because of these 2, the atoms getting added now become 4. So literally the thing balances, but it shouldn't stress you. That's why I've just said may. So with or without it, things are very okay. You either put there the 2 if you want, so that for the balancing to come out. But if you don't feel like you're supposed to put it, don't. It's not a crime. About the naming, you know. This is ethane, the other one is ethane. We did nomenclature for either. So I don't think that is a problem. Okay. If someone really wants to see that fake mechanism, I don't usually want to show that mechanism because it is fake. No one will ever ask you the mechanism, so let's write like a fake mechanism. So the things are the same. If you understood the other ones, yeah, you're going to just be enjoying. So you come, attack the first edge. If you have a good handwriting, you put those ones. That one goes off. Real things. Here we shall not apply Markovnikov because the carbons have the same number of hydrogens. So assuming the H goes here, for this to become H2, this will be C. So one bond has been lost. When we are dealing with alkenes, there were 2 bonds. After the attack, we remained with a single bond. Now the bonds are 3. After the attack, that bond goes with the H. You get the point? So we remain with only 2 bonds. After those 2 bonds, this side I strictly have CH. You get the point? Now CH, you all know that this carbon will have a positive on it, isn't it? it will have a positive because it is having 3 bonds which are less, making it unstable, uncomfortable. We put a positive on top of it to show that it is not okay with whatever is happening in its life. Then the other H went off real things, H minus. And these are statements I was mentioning before. So what do I have here? So this H minus, someone can really come. You all know the direction of electrons from the negative charge to that carbon atom with the positive charge. There is that force of attraction. And what do you get after this? You get CH. The double bond is still there. Then you have CH2, like that. So because our target is to get an alkane, we cannot allow our mechanism to stop there. We shall now bring another hydrogen. That's why I talked of the balancing so that people can get it, that the hydrogens are 2. But since I said may, with or without it, your work is right. You get the point. So I put there to say that when I bring the second hydrogen in the mechanism, people are not confused. I hope people know why I put a 2 there. So we shall come and attack another hydrogen. So here I have a very poor handwriting. I will not put the partial charges. I'll just leave it like that. That one goes off. Then what do I get? So assuming this time round, so this has been now a double bond. After the attack, they disappear completely and we remain with a single bond. I don't want you to be weird people who are going to make electrons come from a single bond so that you remain with a space. That one doesn't exist. I told you that the source is strictly multiple bonds, which are the double and triple. So assuming this one is left as it is, so even here the carbons have the same hydrogens. So the H will go where it wants. So assuming this time round, it goes to the last one and it is CH3. So you see, I've not exposed the single bond because I warned you, don't expose single bonds which you're not going to use in the mechanism. Only and only expose those you're going to use. I said that. So the last carbon is okay, but this first one is not okay, and we shall give it a plus. So we shall put a plus on it like that. But remember, this H went off few things, that one. So it is this side as H minus. So when I come and put here my H minus, I get the answer. CH3, CH3. I think that perfect mechanism. You can do this mechanism as rough work very fast. So for those who are always confused about the products, you can always first sketch the mechanism. If it exists, then you get to know your product. But in case the question doesn't want the mechanism and it really wants the product, have the other knowledge that when I add hydrogen to any alkyne in presence of nickel or the others, I'm supposed to get an alkane. And when I'm to compare hydrogens, I want you to look at this. This one was C2H2. But when you look at your alkane, it is C2H6. And this is the difference I've been talking about here. That this one, ethane, has 2 hydrogens, but ethane has 6. That means 4 have been added. Yes, 4 have been added, but the hydrogen you're adding is just H2. But in organic chemistry, there is where balancing is key and there is where balancing is not a must. We shall keep guiding you. So if you really want the 4 to come out, the 4 that has been added, you show these people that 2 molecules of hydrogen have been added. Remember, just one molecule, H2, has 2 atoms. That's why they always tell you that hydrogen is diatomic, or it's a diatomic molecule because it has 2 atoms. So if you want to really add 4 atoms of hydrogen, you're supposed to add 2 molecules of hydrogen. And that's why even in the mechanism, the 2 molecules were used. Someone may be like, where are those 2? The first was used here. That was the first molecule. Then the second molecule was used there. You get the point? And the mechanism was complete. So that has been something about the symmetrical. Let me get something asymmetrical. But there is no change. No change at all. Let us call the name of the reaction 1 so that the first application is part A and the second is part B. So here, you all know that the moment you add a hydrogen, you all know that the moment you add a hydrogen, in presence of nickel, at 150, if you don't do that, you can use hydrogen in presence of platinum. But since we are supposed to go to an alkane, 2 of the hydrogen molecules are supposed to be used, so you can put a 2 if you want. If you don't use platinum, you can use palladium. And we agreed these things happen at room temperature. You can leave it like that, or you put room what? Room temperature. Standard abbreviation, RTP, with the dots in between. And that is it. So at least you now have all options, whether to put a 2 all note, whether to put room temperature all note. I told you avoid 25 because someone can literally forget that room temperature is 25, but have it in mind that it is really 25. So since these carbons are 4, we're having our triple bond there. So we're having 1, 2, 3, 4. The carbons are 4. That means even the alkane we are forming should have 4 carbons. And you all know CH3, CH2, CH2, CH3. I remember teaching you nomenclature very well. We agreed this one is but1-ine, something I'm not ready to repeat. This one is simply butane. People prefer calling it N-butane, those who have read textbooks, but the best is just butane. So the effect mechanism is the same. Just because here the effect mechanism may involve some sort of what? Markovnikov. So you people here, they are basics you're not supposed to forget. Do you remember when I taught you the cheat code of mechanisms in Alkane's lesson 2? That's where most of the information is. That's why that lesson is 5 hours. Because on top of what was supposed to be taught, I gave you the cheat codes and behind the scenes. That's what happens in most of the mechanisms. In most of them. Okay, now, um, very first, let me show you the effect mechanism. So I've dealt with people who may want to learn how to get the product without stressing themselves with the mechanism. So you just need to know alkynes hydrogenate from alkenes. The effect mechanism may involve some bit of Markovnikov. I remember telling people that if the functional group is a carbon to carbon triple bond like it is here, if they tell you that a reaction is taking place, that thing must disappear. So we should either make it a double bond. If it transforms from triple bond to double bond, it has changed, and that is it. If it becomes a single bond, well and good. Provided we have that change, that it was triple, it's now double. It was triple, it's now single. Provided that change is there, that simply shows that the functional group has literally participated in the reaction. And that's what is required, nothing else. So very first, we all know if we are to balance, the hydrogens are 2. This assists us in the mechanism, so that when I bring the second molecule, people don't ask, but why, but why? So let's attack the first molecule. I don't have a good handwriting, so I'm not going to show the partial charges. One goes off. Should try your level best to show that the arrow is interested in the edge. Something like that. Okay. Now, because of Markovnikov, we are having this carbon and this carbon. But this carbon is more lucky because it is having this hydrogen. For it is having that hydrogen. So that means hydrogen will prefer this carbon that is at the end. Yeah. And you all know every time we have such an attack, what has been a triple bond, it meanwhile becomes a double bond. So right now we are having a double bond, and this last carbon of ours is CH2. So when you look at that last carbon, it is sorted. It has the 4 bonds complete. But this carbon of ours, the third, is not okay, and it has a plus on top. So the other H of ours went off few things as H minus. You get the point? Yeah. I want to teach people a certain technique that you will come across. You find people putting here a plus. They put it down. And why are they putting it down? Because they want to show things at once. It's a very wrong, it's not wrong, but it is long. That's what I wanted to say. It's a very long arrow. You may find certain people criticizing it, but of course it is somewhere in textbooks. So in case you're given a paper and the space is not enough for you, or you're being fast, you get your marks. Because it is clear, this was an intermediate, this was a product on its own, they interacted. You get the point? So what do you get here? I have CH3, CH2. Now, the moment you do this mistake, you're bringing problems. That means you dodged the previous lesson. I told you it's better you expose that edge and put it as a branch. So I'll come and put the edge here as a branch. Then I put my CH2 here. Then after that, I can now bring the what? The second molecule. So we attack the second molecule. So this time round I have a good handwriting. I will include the partial charges. Make sure that bond is not very long. When bonds are very long, chemistry has it that they are very weak. And we don't like that. So when that happens, this is what we have. We shall have CH3, we shall have CH2. Now the bond has disappeared, but still this carbon is having more hydrogen. So it will take the H. So this carbon will remain CH, but now this one will be CH3. Get the point? But again, it will have its plus. So we are going to put the plus down because we want to repeat the other same thing. I told you organic chemists are designers and they are not perfectionists like those of physical. This one is H minus. And we have agreed that we shall have that arrow. The arrow is not easy. We shall draw it. That one. You find it somewhere in the future. So this one had some bit of Markovnikov here. And you can see the format is not changing like that of alkenes. The only thing we are having here that we are going to be introducing a second molecule always. But that thing of introducing a second molecule should not bother you. It shouldn't bother you. The criteria will remain the same. Attack the H, let the other one go off, let them work together, get a product. As simple as that. So that's what happens. That's what basically happens. I remember teaching you how these things are revised, and I'll give you the same advice as the end of the lesson. That whatever I'm now going to use in may be halogenation. Those examples, you're supposed to come and shift them to these ones of part A, like that. Just keep on shifting and shifting. So that is all with hydrogenation. People are so quiet. I don't know why. Let me see what people have in the chat. Okay. So you people, you first tell me, are we okay there? Are we okay? Is hydrogenation okay? Let me even pinch the screen well. Is hydrogenation okay? We go to the next thing. Is hydrogenation okay? We go to the next thing. Are you okay with hydrogenation? Okay. Now, that is good and thank you for following. So note, the above hydrogenation, the above hydrogenation yielded alkenes. But what if? What if we need alkene? You know, the people are getting it. If you look at those mechanisms, let me pinch for you the screen again. You realize that somewhere in the middle, we have alkenes in our mechanisms. Yes, the alkenes are part. So someone may be forced and be like, if this is really happening, can't we really have formation of an alkene from an alkyne? Like maybe we should make sure the mechanism stops somewhere so that the mechanism does not go to completion, so that we also get an alkene. Why are we straight away getting to the alkane? Yes, yet we pass via an alkene. Isn't there any chance of having an alkene? The chance is there. The chance is there. And this is the reagent. The reagent is still hydrogen, does not change it. Then the condition is called Lindlar's catalyst. The chemist was called Lindlar. That was the chemist. So Lindlar gave us a catalyst that can help us there. So because the chemist was Lindlar, the catalyst is called Lindlar's what? Catalyst. And that's how you write it also. That's what you write in papers. Lindlar's catalyst. As it is. That's what you write. Then the most important thing here is this note. This is the note that usually gives people hard time. Lindlar's catalyst. Lindlar's catalyst. Lindlar's catalyst only works on alkynes, only works on alkynes, only works on alkynes with the 4 carbons and more. Only the mere fact that I have begun with 4 carbons, that means this is the least. But I also warn you. I also warn you. I also warn you. I'll tell you some books force it on propane. Remember, propane is 3 carbons. Some books force it on propane, but me, I'm not going to use it. I'm going to use the most correct statement, which says Lindlar's catalyst only and only uses or deals with alkynes which are having at least 4 carbons, 5 carbons, 6 carbons, 7 carbons, like that. So don't ever risk. Don't ever risk and use ethane and Lindlar's catalyst. You're doing a very big mistake. Even when some books force Lindlar's catalyst on propane of 3 carbons, I don't advise. Personally, I don't advise. But if it is 4 carbons, that one I agree. Propane not what? Not advisable. So this Lindlar's catalyst, it has its contents, but you don't need its contents, and I'm not going to waste your time. It has contents, those things of palladium, poisoned with blah blah. You don't need that. You don't need its contents. Do you know those things of food tests? Those things of food tests, those ones twice, they just call it the Buretti's test, Benedict's test, because they don't want you to stress your soul. They don't want you to know what really Benedict is having, what Buretti's solution is having. There are those other things. That reagent, the one that is blue, they use to test vitamins. They just tell you it is DCPIP, but they don't tell you what that is. And that's what is usually done at high school. You're going to come across so many things in organic chemistry. They tell you things like Fehling's solution, Lucas reagent, Ptolemy's reagent. They are not going to tell you what they really contain, but they will be marking your work. But of course, you're going to be guided throughout. Personally, I will guide you. But those lessons are already there on the Senior 6 folder concerning which words are accepted, which words are not accepted. So the same with Lindlar's catalyst. Even when they give you the contents, please don't concentrate on them. They will come and tell you, okay, it is literally hydrogen poisoned with palladium. There is some limestone, which is calcium carbonate, and there is some quinoline. But you don't need all that. You don't know what quinoline is, so why do you stress yourself with that? But you don't need its contents. So how do we, or how are these things going to look like? That's the question. Okay, how are the equations going to look like? You know the reagents, you know the conditions, and you know that we are dealing with a minimum of 4 carbons and maybe more. This is it. So we are having those are 4 carbons, symmetrical. How many are those? 4 carbons still, but symmetrical. Then those are 5 carbons asymmetrical. So when you come and in each of them you put hydrogen on top, then you can put Lindlar's catalyst down, or you can put them in the same line. Lindlar's catalyst, we all know it helps us to get alkenes. So it's like the Lindlar's catalyst is there to make sure the reaction does not go to completion, that the reaction does not finally give us alkenes, that it stops somewhere at alkenes. So this first one, CH3, CH2, I told you alkenes. I think that is very okay. You just keep the position of the bond, yeah? Then here, you all know, you must always expose that carbon to carbon. Here you can put the H there, for reasons I explained. CH3. Then this last one, same thing. Just maintain where the bond is. CH2. So you're going to put the double bond here, then be like CH3. So that's what you can do first. Then be like, I've added hydrogen, 2 atoms. One atom goes here, another one goes here. But I told you it is very important to expose this hydrogen. Why? You're supposed to expose the bond. But this hydrogen I've circled in blue, you may not need to expose it, but rather just put it in that space. When you expose it, it is okay, but may I call it designing? But for it, it is better for it to occupy that position because it is no problem. But this first one, again, you cannot put it at the back. That is again being weird. I warned you about all that and I'm not repeating. So let me hope people are okay with that. People, are you okay with formation of alkenes from alkynes via Lindlar's catalyst? Because now we are moving. Are you okay with that? We proceed. Are you okay with that? We proceed. Hey, these days people are serious. Yes, Camila. Camila has something to say, I think, before we proceed.
Yes, teacher, I have a question. So,
Mm. Before you ask someone, I'm seeing someone asking for the screenshots. So you can take them. You can take the screenshots. It's okay. Yes, proceed. You ask.
yes, so from the discussion right now, we are saying that if we want to get alkenes from alkynes, we consider using Lindlar's catalyst, and
Mm.
that is for the hydrocarbons with 4 carbon atoms and above. So,
Mm.
in case we want the ethane and propane to stop at the alkene level, what do we do for them?
What do you do?
Yes.
You go through other series of reactions. You understand? Which series of reactions we shall see with time. That's why me, I'm not teaching you anything like synthesis because I know when best that is supposed to be taught. So there's what they call synthesis, where we synthesize certain compounds from other compounds. So when you want to move directly from ethane to ethene, that one is not possible. But you can go through some weird pathways and finally get it. Understood? Hope you got it, but you're off. So you take that screenshot as well. You take that screenshot as well. I know you people are going to read books and they are telling you you can simply add the hydrogen and the mechanism stops somewhere in the middle. No. The moment you add hydrogen to one alkyne, it is alkane, no alkene. Lindlar's catalyst does not work on ethane and propane. Yes. Mm. Okay. Now, we are going to let's check the syllabus book because as if we are slow. I don't know why. Are we really moving? What are we doing? Hydrogen is done. Okay. After hydrogen, we are now going to handle halogens. Then acidified water is yours. Yes. Acidified water is yours, and that will be your 5%. It is yours. Then there is what they call hydrogen halides. Those ones are going to come after halogens. So let's do halogens. Then we later go for hydrogen halides. Okay. Now those who are with me, addition of halogens, of course, is what they call halogenation. Addition of what? Halogens. That's what they call halogenation. And I remember teaching people here two conditions. I don't know if people really recall. I remember telling people that the halogens have the format X2. And in these mechanisms, we basically concentrate on Cl2 and Br2. Then I remember telling people that this X2 and blah blah is the reagent. Then I continued and told people that this reagent may work under two conditions. There are conditions where we bring what? CCl4. Then there are conditions where we bring the water. You get? And I remember telling people, someone tell me, this, assuming this is case 1, let me see if people really recall. This is case 1, and this is case 2. Who can tell me, where is X2 pure? Case 1, case 2, with reasons. Who can unmute and tell me? That person who attended that lesson and understood. Who can tell me? Of case 1 and case 2, where is X2 pure and why? Mm. Mm-hmm. We said addition of halogens is what they call halogenation. So the reagent is the halogen, which is X2, Cl2 or Br2. The others we are not interested, but there are other halogens. So this reagent works under different conditions. You get the point? And I remember telling people, this carbon tetrachloride is like the condition, because X2 we have agreed it is the reagent. And I also added that this water is the condition. Isn't it? Let me see, as if someone has something to say. You people, no one is saying anything in the chat. You see, people, you don't want to read. You don't want to read. You don't want to read. So no one has an idea about which one is pure and which one is not. Let me hope, Lama, you're going to give me the right reasons I gave. Yes, Lama. Yes, Lama.
Okay, so for me, what I recall is
Mm-hmm.
you said that
Mm-hmm.
the X2 stroke Cl4
Mm-hmm.
is pure because
Yes, that is right.
because the Cl4 is dry.
Yes, thanks for trying. I said because this one is not going to participate in the mechanism, not so.
Yes.
And I used the word inactive.
Yes, teacher.
I also remember telling you that it is an inert solvent, not so.
It is.
Yes, thank you for recalling that. So because it is inactive and it is an inert solvent, it's not participating in the mechanism. So we are going to have purely X2 participating. You understand? Inert solvent doesn't participate in mechanism. That's what we said. Okay. Then all those others that also followed, remember telling you that water is a universal solvent. So you cannot bring water as a condition and it fails to participate. There you're deducting its aura points, and it cannot actually accept that. It's a universal solvent. The moment you make it part of the reaction, it must participate, you like it or not. So for this water, it is active. Why is it active? You all know it from primary. That water is a universal what? Solvent. You get the point? Now I usually forget, and I don't want us to get issues in the next session. I lost one of my pens, the ones I use in these classes. So immediately after this lesson, I need someone focused to remind me. I usually recall at night when those people have closed their offices. And when you send a message when the offices are closed, when they open the offices, they don't get the message. So I'm supposed to send the message during the day so that we order for another pen. Otherwise, we may soon get issues if I don't order the pen as early as possible. So after this lesson, someone should remind me we get that device. If you'll be listening to a recording, this is none of your business. And I'm not being rude. Okay. So, universal solvent, so it will literally participate. Yeah. So water will eventually participate. So participates in mechanism. And we are going to see how. And trust me, they are the same steps. This case one is the easiest. Easiest. I don't know. How can I call it? Let me call it capital A. This case capital A. Then let me call this case capital B. So that those who take screenshots will have a sense of direction. So very fast. Case A. So you're going to begin with let me use copropine here. Get the point? And what are we adding? We are adding, let us begin with chlorine in presence of CCl4. Now, the product that is formed may confuse people. But as I said, you all know this one is not participating in the mechanism. It is out. So don't even think about it. And you all know if the mechanism is to happen, the whole of this must disappear. Because it is the functional group and it's what participates in the mechanism. What is the proof of participation? Loss of the triple bond. I said all that in the lesson of alkenes. Now this is it. Assume it has been lost. That's what you get, isn't it? Because this one is not participating, the inert solvent, it is not participating, isn't it? It is not participating and the triple bond must be lost. So if it's lost, what remains is a single bond, and we said no need of exposing single bonds. If you're not going to use them, you are wasting time and you're making errors. So that means we shall have something of the sort. So when you look at this carbon, it is lacking, this last carbon, it is lacking two bonds, isn't it? For it to be stable. Even this one in the middle, it is lacking two bonds to be stable. You know that people I'm teaching you how you're going to come out with the product without you first struggling with the mechanism, because you need those techniques. I've said CCCl4 is a inert solvent. It won't participate in the mechanism. If we are really saying propine is reacting, its functional group that defines its chemical properties must participate. What is the proof of participation? Loss of the triple bond. It should go away completely with no hesitation. And when I try to write a sketch, a skeleton of what we shall have when the triple bond has been lost is what is present in orange. And when I try to find out how many carbons are non-stable, they are the last two, where each of them requires 2 bonds for it to be completely okay. And who is available to fill up those bonds? It is this guy. It is only that one, no one else. If I don't want you to be like, but doctor, you told us it is hydrogen that usually fills them up. My dear, we are not dealing with hydrogenation and we are not dealing with isomerism. Right now, it's a reaction. So if it's a reaction of adding chlorine, if in the product you're having hanging bonds, you like it or not, it is chlorine to fill them up. So all those hanging bonds will have chlorine. Cl, 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 Cl. And that is the answer. That is the answer. About its naming, we are going to see it in the next topic. Because I know someone wants to say, hey, doctor, how are we really going to name this? These things are the easiest to name if you have been following up our nomenclature from scratch. So how it is named, it is coming in the next topic. The IPAC name, so people tell me in the chat, is how I've come up with that structure okay before I even take you through the mechanism? The IPAC name, we shall meet in the next topic. Friends, is that okay? Is the structure okay before we go through the mechanism? Okay. The mechanism is okay. Now, the mechanism, it is the easiest. Nothing new. That's why even the syllabus book, those people were open that how things happened in alkenes is how things will happen in alkynes. They may even never wanted us to teach you all this, but of course we shall tell with time. I have that. You all know. So I ignore the inert solvent. So I just deal with the Cl alone. So someone, I don't know if people are seeing the same case happening, that our Cl2 we are adding, it's only having 2 atoms of chlorine, but the product is having 4 atoms. That's where balancing comes in. So I will force myself to put a 2 here, but I told you it is not a must. I repeat, it is not a what? It is not a must. These 2. It's just there to balance. Because when I put 2 before chlorine, the atoms become 4, which 4 atoms are the ones in the product. But I said you may or may not. You may or may not. The perfections you will put, those who don't care will not. Why I'm saying that, you'll find different people telling you different things. Someone will tell you, do this. Someone tell you, do this. But I've told you, that's not something key in organic chemistry. You may or may not. So mechanism. So, shall have our Cl dash Cl. Should I have a good handwriting? I'll put it. And you know that one will go off like that. Same things, Markovnikov. Markovnikov should work because when you look at the functional group, this one is having more hydrogens. So you like it or not, it will take the first chlorine. I told you Markovnikov does not only work on attack of hydrogen, even halogens. They go for the richer carbon. Yeah. So what has been a triple bond, you like it or not, it will remain a what? A double bond. Then this one will be H, then Cl. People, you do what you want, eh? You can either put the Cl on top as a branch. Someone may want to put it there. It is very okay. But you are exposing a single bond which you're not going to use in the mechanism. So you can write it like that, or simply put the Cl here. It is very okay. So the last carbon is okay, but this carbon in the middle is not happy. So we shall give it a plus on top like that. Then you are all aware that we lost our Cl real things. It got lost like that. You get? Then after that, I'll bring it Cl with the minus. I attack that carbon. And then I'll come up with something stable. You see? Cl, the double bond is still there. H, this one is Cl. You understand? Yes. But according to the balancing, you realized we are supposed to use 2 molecules of chlorine. So I now bring the second molecule. So someone may be like, what if I've not balanced? Am I really supposed to bring the second molecule? Yes, because you know the bonds must completely get done and you only remain with single bonds. So when you still see a double bond, you bring another molecule to be attacked without inquiring from anyone. So today I have a point writing. I'm going to put the partial charges. That's what we have. Yeah. So what we get after here is something like this. CH3, Cl. That chlorine will still go to the carbon with more hydrogens. So still this carbon will be favored because it has 1 hydrogen, this one has none. Get the point? So that bond will disappear, but my dear, you're not supposed to expose it. You're not supposed to expose that single bond because you're not going to use it in the mechanism. So straight away bring the H. Cl like that. But remember, you've added a second one, so you can make this 2. Do you get the technique? You can make that 2. Or if you don't want, you can literally come and put it here. Be like, this is my Cl. That one is okay. Or you can just say, after all, the Cl has been added to the same carbon. So the Cls are now 2. So I put here what? A 2. Then we have lost the Cl real things. Cl minus. Then this one has a plus. It has a plus. I don't want you people to do weird arrows. These arrows facing down. That is weird. If you feel like it is going to be too much, just simply come here down. You rewrite your Cl with the minus. Don't put it very far. Do that. Get the point? Then get your product. This is organic chemistry, provided you show the arrows. Arrows are there to show us the direction. Now here I want to teach how this thing can be compressed. Now you're having CH3, you're having C, and the C is now having 2. Could you try again? And now the C is having 2 chlorine, so you can come and write Cl2 like that. Then the last one is CH, but it is also having Cl2. So this is the compressed one. In the equation, we have what they call the graphical one. By graphical, they mean those structures that expose most of the bonds in the structure. You see that? So here we have compressed everything. That's why you're seeing these twos here. That is a 2 and that is a 2. But in the product, we had something graphical where most of the bonds were exposed. And you people, I don't want people to set this and you fail, because these are 6 marks. In UNEB, when they set, if they deny them marks, they give it 5 marks, but they're usually 6. They give the product a full mark. They give this first attack a mark. You are aware the other CL that goes off is marked here separately. This intermediate is marked. This attack is marked. This intermediate is marked. This attack is marked. The other CL going off is marked here as a product. This intermediate is marked. This product is marked. You count those marks. You count them and put them in the chart. And you see the scores you're joking with. And to make matters worse, I set for you this item. The item is there. You find time and read it. You go to the drive under e-library, under assignments. You look for the 4th assignment. I asked this very thing. Yes, you're going to see it. And this, I wanted this mechanism somewhere. So I expect people to go and handle it very well. I usually love it when I teach students and hand in their work when it is marked. That's what I usually do. When I give you work, like these things of mechanisms, hand it in when it is marked. Because I believe you've heard where the marking points are. There is a vitamin you get when you start marking yourself and the work is okay. There is that confidence you get, and it is so important in question attempt. So people, are we okay with that mechanism? You people, you are quiet. Why? Are we okay with the mechanism? Okay. Now, that was for case A. I believe you people can now do BR. You people, do I need to do BR really? Because BR, wherever there is CL, you remove CL and put BR. So do I need to do BR? Do I really need to do BR? And you people, I've actually done Markovnikov, which is the hardest. If it is symmetrical, the CL goes where it wants. After all, the carbons will have similar groups on either ends. They'll have the same hydrogen. So if it is symmetrical, I think it is the then. You people, do I need to do I need to do BR? Do I need to do symmetrical? So these are the comments I expect in the chat. You say BR are not necessary, symmetrical not necessary. If they are necessary, you say BR are necessary, symmetrical necessary. Why I'm saying BR is not necessary? Because it is the same thing. We are just removing CL wherever it is and we are putting BR. And for symmetrical, why I'm saying it's not necessary, that for it, as you attack the CL or BR and asking yourself where it should go anywhere because these carbons are literally the same. What is sensitive is about Markovnikov. You get that we are supposed to go to the richer carbon. If both are not necessary, you say both not necessary. If both are not necessary, you say both not necessary. But if you feel like one of them is necessary, you say it. I want to follow you people. You represent your friends in the future. So you represent them well, please. So I'm waiting for what people are saying. Most people have said both not necessary, and that is very good. That means people are following. That is nice. Note. For ethane to undergo similar reactions, hope you know why I've been not talking about the mechanism with ethane. Because ethane is a last bond in these things of alkynes, so it is a bit picky. So for it to undergo similar reactions, something funny must be done. You must bring in a catalyst. If you don't bring in a catalyst, I assure you, it will not react. Why? It is the last bond of alkynes, so it is a bit picky. Yeah. And you know last bonds. So for ethane to undergo certain reactions, it needs a catalyst. Someone may be like, yes, we are getting a catalyst, but which catalyst exactly? And what is this catalyst going to do? You know, catalysts, they speed up the rate of the reaction. Yeah? A catalyst must be used, and as well, iron what? Iron filings. Most of you make a mistake and filings, you write single L, yeah? But it is double L. So someone may be like, what are these iron filings going to do? These ones are there to absorb heat during the reaction. Someone may be like, why didn't we add them in the reactions before? Do you mean we didn't need to absorb some heat for the past ones? This one is specific. Why we need to absorb some heat? It's because the reaction with ethane is explosive. The reaction with ethane is what? So you people, do you need do you now see why the last bond needs a lot of attention? Because its reaction with those things is too explosive and dangerous. So if you really want it to happen, bring two things: iron filings, which are going to absorb the heat, because we are talking of explosion, so we expect some heat to be released. So make sure iron filings are part for that heat to be what? Readily absorbed. Why do we need the catalyst? The catalyst is needed to speed up that reaction so faster that it does not cause a lot of issues. Because catalysts are there to speed up the reaction. And of course, some other uses of catalyst, you see them in transition elements. That is senior 6 term 3 topic 11 subtopic 3 term 2. So catalysts are there to speed up the rate of the reaction. So the catalyst you're supposed to use, you either use a metal halide, catalyst. If you don't use a metal halide catalyst, use this one. And all of you can name this, yeah? I taught you this in Think chemical formula. That S is silicon. You leave some space. This 2 means di. And the O is for oxide. So you can use that one as the catalyst. But as you know, chemistry things, they always use those weird names to confuse you. So you find people calling that catalyst a very weird name. I don't usually want to pronounce these things because people may judge me and they may use those things as weapons against me, but that is the name. These are things that are good to know. Let me tell you, an exam cannot give you such information. But most of you are going to do industrial chemistry, and it is a very good course. So when you do industrial chemistry, I'll be part of your foundation as far as your future job is concerned. So that is the name of the silicon dioxide catalyst. I don't want to pronounce it because some of you are Baganda. If I tell you that this one is silent, you may not accept. But you go to Google, ask Google pronunciation of that. They pronounce, you go with that. And that's my similar pronunciation. So that is it. That is it. What have you people realized? That for ethane to react with chlorine or Br2, issues. Which issues? Explosion. Meaning a lot of it is going to be released. So the reaction may be a bit hard. But if you really want it to happen, bring iron filings to absorb the what? The heat. Then add a catalyst that will help us with whatever we really want to do. The catalyst should come up to speed up the reaction because we have there a certain unstable intermediate. Unstable intermediate. I will teach you those things. If you don't want to bring a metal halide catalyst, bring the silicon what? Dioxide, which has that other name. So how does the equation look like? Or how will it look like? This is how. This is how. That if that is your ethane and you really want it to react with chlorine, for it don't bring those things of the inert solvent. Just provide the iron filings and just make sure your silicon dioxide is available. When these people are marking you, they will mark the reagent, they will mark the condition, they will mark the condition. And how are things supposed to look like? You know, if we are really reacting an alkyne, that is supposed to be lost. So we expect something like this, C, then H. So each of those carbons is lacking 2 bonds. Put Cl here, put Cl here, put Cl here, put Cl here, like that. And that is the final product. And if you're this person who doesn't like designing like me, you can compress this. Compress it. And when you compress it, what will you have? CH, then Cl2, CH, then Cl2. You see, that one is also okay. Provided things are single bonds only, for you just compress them the way you want. The problem comes if somewhere we have double bonds or multiple bonds. You should respect that too. So there is something that I want to comment about this mechanism. What really brings about those things of explosion, the instability we are talking of. You all know we are going to first attack the Cl like this, isn't it? And then we are going to come up with, agreed, now it's going to be this kind of bond. Then we shall have the Cl somewhere. So it will be a plus. This one will be Cl minus. Cl minus will come. Then you will have something like this. So this thing is very deadly. That thing is very deadly. Very deadly. Very deadly. Very deadly. Very, I repeat, very deadly. And that's why we really need a catalyst, so that we pass by it very fast to speed up the reaction, but it is very deadly. Very, very deadly. On top of that, this one is also very unstable. Of course, you know it is unstable because of this plus, but this one has no plus, but it is very deadly. That's why we need to handle the last bond very well. It is deadly for its own reasons that you don't need at this level, but at least learn it too, that it is deadly. So that's how things are supposed to be written. You'll find different arrows, but I want you to be students who are good. You find such when the ion is down and this one is here. You'll find some other time where the ion and this one are on top and this one is down. You get, you'll find when these two have been, when they have changed positions, just be those students who are flexible with the organic chemistry, because it's not for perfectionists. So let me hope we took that screenshot. I don't know, did we? You take that screenshot? I think we never. You take that one of halogenation. Very fast, you said it was okay. Then take this one of ethine. So you people, you confirm to me that ethine is okay. You just say we are fine with the last bond. You say we are fine with the last bond. You say you're fine with the last bond. So this is alkynes lesson 2. So you assure me that you are okay with the last bond as far as how it must react with the Cl2 is concerned, or with generally the halogen. People, are you okay with the last bond? People, you have been good people. You're not giving me comments. I don't like that. You be fast. Even before I complete my question, I beg I receive the replies very fast. So you people, you read different books, they'll tell you a lot of things, but I've warned you early enough, yeah? To avoid that confusion, just be good students. Now, the other thing I want to tell you, you will find books. You'll find books. What will these books say? They will tell you that the whole of this is the catalyst, yeah? When they tell you that, don't be confused. Like, but they told us something different. But that is for industrial chemists and doctors. Yeah. For those who are going to become teachers, you only need iron stock that to teach your students and pass. So don't be worried when they tell you the whole of that is the catalyst. Now, we have case B, which has water. So I want to tell you this for case B. That concerning alkynes, is a very rare reaction and dangerous. Very rare and what? And dangerous. And I want to give you very strong, and I will tell you, may not be examined. Yeah? You people, it's not about us knowing the theory. Eh? Some of the reactions that seem explosive in the lab, dangerous, hazardous. In one of the textbooks, they said hazardous. So even when the mechanism may theoretically come out, it's not a must that something is supposed to be taught, but it is a very rare reaction. Because now this one needs to participate, even the water has to participate, and the alkyne is having a triple bond. Yeah? Are you seeing how the reaction is compacted? It is a triple bond. We must reduce it first to a double bond, then later to a single bond. There is a battle between X2 and H2O. Like very rare, very dangerous, hazardous, very complicated, very compacted. So it may not even be examined. But even after telling you all that, I will advise you. What is my advice? Practice the mechanism. Practice it. Practice the mechanism because I know you know what to do. Copy. Copy what was done in what? In alkenes. Yeah. Practice that mechanism. Copy what was done in alkenes. Just like you realize we have been just borrowing ideas. So also borrow ideas and do that. But it is very rare and dangerous. It may, I've said may, don't say I said it will never. It may. If the wiser can set it and you followed my advice, you're good to go. Remember I told you everything I give you as research and advice, make sure you get time and your teacher at school, your favorite teacher looks at it so that they can tell you the last words. Yeah. Now, I'll come here and tell you that also halogens, I'm done. So the next thing we are handling are the halogen halides, and you all know how these halogen halides look like. So 3 halogen halides, sorry. Hope that's what I said. And you all know they're in the format H what? HX. And we agreed now for this one we always use HBr, use HCl, we always use HI, yeah, HBr, HCl, and we also use what? HI. This one is the easiest. The only difference here are the conditions. That for alkynes, the conditions are going to change a bit. Same as alkenes, but conditions are adjusted a bit. The conditions are adjusted a bit. The conditions are adjusted a bit. So what are those conditions? The condition is what? UV light, nothing else. UV light. What is the condition? But if you feel like you're not okay with UV light, you can use copper 1 chloride catalyst. When they tell you copper 1 chloride catalyst, myself, I taught you chemical formula. Myself. So you all know how it did look like. It will look like this copper 1 chloride catalyst. But you people, hey, copper 1 chloride, chlorine has valence 1. So it will come up like this. But I want to assure you, this one can exist as a dimer. I know you people have ever heard of polymers. So when I say it can exist as a dimer, this is what I mean. Yeah? So when you find it, don't be surprised and be like, how come Dr. Po didn't tell us that? I'm telling you right now. So a dimer is this. And how is it written? They open those brackets and say Cu2, Cl2. But the name is the same. Same name, yeah? Copper and chloride, just because it has exited as a dimer. Like two molecules of copper 1 chloride together. You come up with something like that. So when you find a book where it's written like that, don't be confused. But what is this? It is a condition for the alkynes to react with those HXs. Either use UV light or a catalyst of copper 1 chloride, which has two formats of being written. You get? Things are not hard. These things are not hard. So for this one, I can even begin with our ethine, because this time around it's not going to act weird. This time around it's not going to act weird. So I can decide to begin with just begin with HCl. Then here down we put UV light. You get? You all know, since it is the alkyne reacting, the whole of this must what? Must disappear. So when it finally disappears, we shall have something like this. And each of the carbons will be left with two hanging bonds, isn't it? So the question is, who is going to occupy those hanging bonds? Because this thing is symmetrical, this, H will first come, maybe it goes here, then the Cl will come. Where will the Cl go? It will come here. Then another H comes. This one, I have no way of teaching you. For me, I know it as a person. But for you as a person, you may not know it. And that means this one will purely depend on the mechanism. Hey, this one, let me tell you point blank. It will disturb most of you. You will only understand it in the next topic. Hey. So I will say, meanwhile, no shortcut. Meanwhile, no shortcut to product until next topic, and which is that topic, alkyl halides, to the next topic, which is that topic, alkyl halides, is what? Is done. Why? The product there is an alkyl halide. So for this thing, we are going to first write the mechanism. So I'm going to put the product there. But let us begin with the mechanism. Oh, that is very good. But the mechanism is easy. Don't even think it is hard. So you're having HCl. But people may say, hey, but doctor, you want HCl too much. Okay, let me use Br. So I'll come. So today I have a good handwriting. And I'll put partial charges. Don't forget that arrow. This one goes off. So this one will remain as a double bond H. So the B, we are getting H. So the H may add itself on the last one. You get that it becomes H2. Then the Br has been lost real things, so it will be like that. Then this carbon of ours has been left with a positive, not so? So now the Br comes with its negative and touches that carbon. You understand? And what do we get after? And after there, shall have that one, Br. Then we shall have CH what? Sorry, our bond is still there. Here the Br is just touching the C and those two charges are neutralizing. So we shall have our double bond there. Here we shall have our CH2, isn't it? And since we are aware that we are supposed to lose the bond completely, a second molecule will come. And because I'm bringing a second, okay, you people are generally used to this second molecule. It's no longer news, yeah? So I will not say much words about it. So the second molecule will come, still HBr. You see that? Still same things will happen, yeah? Now, are you seeing at this point? Remember, we started, you people, right? We started with our ethane and things were okay. Each of the carbons had 2 hydrogens. We did everything. We gave the H to the last carbon. The last carbon got 2 hydrogens. But now as we brought the Br minus, it went to this carbon. So this carbon was left with only 1 hydrogen. So when this other attack comes in, the carbon that we gave the hydrogen first will have the second chance. You get? So the carbon you give the first chance automatically takes the second chance. Why? The first chance the other carbon you left out gets is the Br or the Cl or the I. I don't know if people can see that. So the carbon you decide to give the first chance will automatically take the second chance. That's why I said, meanwhile, there is no shortcut. That the shortcut is there, but meanwhile, before the mechanism, it's not there. But now after the mechanism, now people know that the carbon you decide to give the hydrogen first will take another hydrogen. I think we shall confirm that in the second mechanism, yeah? So here, what are we getting? So I have a bad handwriting. I'm going to put charges. So here I will have my HC. The double bond is going to disappear, so no need to expose the single bond because I'm not going to use it in the mechanism. So I just have my CH3 here. Because the hydrogens are now 3, that carbon is what will take it because it has more already. So it is sorted. Remember this one, I want to teach you something now here. Remember here you're going to attach your Br as the other product. So you see this time round I've put it on the left. It's not a must that it's supposed to come after. Just be a designer in organic chemistry. Be a designer with concepts. Your work will be nice. So there are two options. Someone may decide to put the Br here as it is and then put here a plus. Someone may be like, when I bring my Br here, remember this arrow should come and touch it like that. Someone can put it here and it must touch it like that. Now, I want to show you something. What if you what if you give things space? But anyway, I will not give people a lot of designing tricks. Let us do what you people have been doing. So you put the Br here. Why here? Because it is better for the arrow to sit there than sitting there. When it sits here, you seeing that confusion is not okay. So to avoid that confusion, you put your Br behind. Because you know your arrow will look good there. You see? Those are tricks of mechanism design. Then you may go up. If you don't want to go up, you have your space. Go here. And then compress things. You can decide to write C, like the way it is. Br, even down, Br, then this one has CH3. Oh, you compress, you write CH2. So you write CH, then Br2, then CH3. This one is accepted. Even compressing is accepted, provided throughout you have single bonds. I used to like writing such things because they used to confuse all my classmates. All my classmates. Because they used to be like, now how are you going to name this? Because this thing is hard to name if you don't first draw the graphical structure. I told you the graphical structure is that structure that tries to expose all the bonds. It is my first time to spend more than an hour on a session and the number is maintained constant. Slowly by slowly, I'll know the time that you people prefer for lessons. I'm keeping my records. So you people, that is it. So the structure, every time you're dealing with these alkynes and you're realizing that the hydrogen is going to be attacked first and the thing is symmetrical. Even if it is not symmetrical, but the carbon that takes the first hydrogen will take the second. You like it or not? So I'm having two people here. Remember, this one is symmetrical. Carbon, 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 and carbon. What if one person, remember this is H, this is H, this is H, this is C, this is H. Let me also make sure they are near to each other. This is H, this is C, this is C, this is H. So I'm saying, what if someone says, let me give my hydrogen the first H, that one, that carbon. So you like it or not? Remember when you give it this first carbon, the other one will take the Br, isn't it? When you bring the second attack, this carbon will have two of them. But this one will have only one. So by Markovnikov, this one will take another hydrogen. And by default, this will take the remaining Br. Do you see that? And when someone begins with this one and they give it the H, automatically this one takes the what? The Br. Now when you bring another molecule of HBr, the H will go to this carbon which has more what? More hydrogen. So hydrogen will be added there. And this one will take the what? The Br. So these two products are the same. I don't know if people get the technique. This is a technique, but the mechanism is there to solve everything. But I also need you to have the technique. Let the mechanism just be a point of confluence, just confirmatory, but also have that technique. That the carbon you give the first hydrogen, you like it or not, it will take the next. So the other carbon will be left with no option other than taking both of them. I want someone to tell me the product I'm going to get here. Without the mechanism, I don't want you to lie to me. I want someone to read it. This time round, I'm using HCl and I'm using a copper 1 catalyst. Anyone to read it without the mechanism? Anyone who can read for us the product without the mechanism? But today, let me use CoHI, so that you also do HCl in the. Let me use CoHI. You see, people are good at cramming. Your brain wants the catalyst to be copper 1 iodide because the HI is hydrogen iodide. You people, anyone to read for me how the product will look like the structure of the product? Anyone with an idea? Anyone with an idea? You people are not easy. You people, this is the functional group. It is the functional group that will participate. This carbon is the carbon that has more hydrogen. So it will take the first hydrogen. So by default, it will also take the other one. That means this carbon will be left with no option other than taking on both I's. You people, aren't you getting the technique? Yes, Simi. Simi is one of my favorite artists. Yes, Simi. But if your voice is not like that of Simi, I don't know what you're going to tell us. Yes, Simi Shalon. Unmute and speak. It's okay, we shall understand. Unmute.
So the product is
Okay.
CH3,
CH3,
CH2,
CH2,
then C bonded
then
to iodine up, iodine down, then CH3.
don't go off. Don't go off. I want to compress this. How should I write it? What if I don't want to design? How do I compress?
Okay. CH3,
CH3,
CH2,
CH2,
Ci2,
Ci2.
CH3.
Have you just learned this today?
Yeah.
That is good. I'm happy.
Thank you.
If you have any balance, don't pay the balance. If you don't have any balance, you're going to inbox me. I send you part of it. Because even your name is good, putting yourself small student. If you have not yet paid, don't pay.
Okay, thanks. I had paid only for chemistry, so they were still demanding me math.
Oh, so don't pay for math because you are a good student who is following.
Thank you so much.
You're welcome. Now someone else is there, but we are also following. Yes, you are following, but you are not live. You are not participating. Someone's like, but we are also participating. You go. So that is it. So you have those tricks of you getting a product before you work on the mechanism. Now let me also cater for my people who depend on the mechanisms, because I was also like that when I was still a student. But that was in senior 4 VAC, because that's when I completed the syllabus. Senior 4 VAC. Hey. Very first, HI. So have a good handwriting. I'll put the charges, partial positive. Sharon, make sure after this you remind me, so that I label you as fully paid. So this one goes off. Sorry, it is I, not H. Hope I'm not tired this early. So you all know this H will go on this carbon because it has more hydrogen, after the other one doesn't have. So from triple bond we shall have a double bond. So this will be CH2 and the to be I negative. So this carbon will have a plus, the other one will be sorted. So this one comes. You see that? These things don't change. I don't see any problem with chemistry. Literally. Like, what is it? Okay. So this is CH3. This is CH2. This is C with I. And so? Then this one is still our double bond. Then we have our CH2 here. And so? Now I'm supposed to bring another molecule of HI. H with my I. Today I have a poor handwriting. I will not put the charges. Just do that. What are we going to have? So it will be CH2. This will be C. Now the H will go to that carbon with more hydrogens, which is still the same as that took the first. So the double bond is disappearing, becoming single. But since we are not using the single bond, no need of exposing it. So I'll put my I here. Now I'll put the positive here. And then the other I minus is lost few things. So I remember giving you a technique. You can do this. Just need to be good people. That is accepted. Very okay. Then you write your compressed structure. CH3, CH2. Instead of CH2 next, we have Ci2. Then CH3. Only single bond, so the compressed structure is okay. Or someone can decide to put this here and they bring there, or like that. That one is also okay. No problem at all. We have also today we have discussed HI. So when you reach the point of using HI in alkenes, it shouldn't give you a time We agreed how to revise this. You just change reagents and compounds with those of 1, 2, and 3. And I gave you a lot of examples in the introduction. So you just keep on picking on those examples, deal with them on the different reagents. Like you assess yourself when it comes to mechanisms. You don't really need me when it comes to assessing yourselves as far as mechanisms are concerned. So literally, even the HI is done. I don't think there is any problem there. So the next thing I'm going to handle, you people have said, I remember giving you research. Let me give you a note. So we have said if someone says HBr UV light, it is okay. When someone says to this and down, it is UV light, it is also okay. Now, instead of two, someone may come and say what? Excess. So when they say excess, don't say but this wasn't talked about by Dr. Paul. Then for the case of the catalyst, they can use. So they can write the catalyst as a dimer like that. So when you see excess, don't say I didn't tell you. When you see the dimers being used, I've warned you. The name is the same. They just decide to be like that. Yeah. Then I remember you giving you research, and I told you to make research about what they call the anti-Markovnikov. Remember, I told you to research about anti-Markovnikov when I was talking of reactions of alkenes. And reactions of alkenes are similar to those of alkynes. So I also give you duplicated research. Yes, you can also go ahead and look for anti-Markovnikov. Markov. That one. I remember telling you in the periodic table that this V can be replaced by F and F, depending on who the writer is and where the writer comes from. But those two are the same, that side. Just like we also have funny replacements this side. Yes, I want to talk about my people from the East, but it may be a bit weird. I may not. It's not good to be violent racially. So you make some research concerning that. Then you do all this in line with alkynes. The other one was for alkenes, but they share reactions. So you'll handle this on your own. Isn't it? That was the deal. Now, I want us to go back to the syllabus book and see what we've not covered, and we comment. So I had picked a certain call, but I'm back. So halogen halides are now also done. So the remaining one is acidified water, but we agreed it is yours. And how is the assignment going to look like? How is the assignment going to look like? Use internet. Use PHET. Okay. This is how I want your write-up to look like. The write-up dummy. So I want you to have the title and be like hydration. It is the one with water, acidified. So it be like hydration of what? Hydration of alkynes. That's why I told you to have discussion groups. So you can be like, in our discussion group, so and so, you are responsible for that write-up dummy. You make research, and thank God that I always guide you. But someone can just tell you, you go and make research about that reaction. But have the title, have the reagent, give us the conditions, then some equations. But the equations here, we are going to be a bit specific. So the conditions, you also give them. Equations, we are going to be specific. We need only two. We need those of ethane, and we also need those of propane. Then after that, show me the mechanisms. For both, It is an assignment. You will enjoy. So hydration of alkynes is this one of acidified water. So it's also done. So they talked of polymerization, but remember this was for alkenes. You get? But here, when the syllabus, this is what the syllabus was saying. I really gave that book time. They just said reactivity and reaction mechanisms of alkynes. Then they said NB addition are the same as those of alkenes. That means we are supposed to look at all reactions in addition to those similar to those of alkenes. You get? Yeah. So that is the simple assignment. So continuation very fast. I think it is part B. There are those we call substitution reactions. And I'm going to tell you where they are. Substitution reactions. You are going to find these ones in chemistry folder. You go. These are substitution reactions of alkynes. I already said you about this video. When you go to the chemistry folder, go to revision and e-library. After that, you go to organic chemistry. After that, you go to organic chemistry facilitation. Then you watch the video. That is the video that has watch the video. Watch the video. You see the substitution reactions. Someone may be like, how shall we know that they are the ones? Those are the reactions they are the ones that identify the triple bond. Yeah? Identifying the triple bond, some people call it identifying, others call it confirming. Yeah? Identification test, confirmatory test. You get? And they are basically two. They are there in that video. I told you, for me, I don't repeat myself. One of them is ammoniacal copper 1 chloride solution. I've just taught you how copper 1 chloride is written. That aqueous is there to show you solution, or they can write it like this. So that's one of the substitution reactions. Like, how do those alkynes react with ammoniacal copper 1 chloride? That video is there, stored. Then the other one is ammoniacal. Now you've learned a new word, ammoniacal. You thank God. There's what they call ammoniacal silver nitrate. That one is another one. It's also a form of substitution reactions for these alkynes. But everything is going to be clear in the video. And these are the two that identify the what? The functional group. You get the point? When they say ammoniacal, it shouldn't confuse you, but I'll talk about it in that video. I talked about it. Ammoniacal simply means aqueous ammonia is present. You people have heard of ammonia solution and so on. When they say ammoniacal, they simply mean ammonia solution is what? Is present, nothing big. So I think you'll watch that video. So when you check the syllabus book, they are talking of test tube reactions to identify triple bond. So I will repeat it here and say, identifying triple bond So I'll say that identifying triple bond see, it is the same video. Please, people, give these lessons time. I endeavor to write whatever is important, and trust me, those things I do, research, assignment, referring you everywhere. You need to be careful. I'm telling you point blank. Now, I will put for you a note here. But they talk so much about that thing of potassium permanganate. Most of you don't know how it looks like. But in that video, it's also present. Yeah? This thing they call potassium manganate 7. This one. Have it in mind that manganate 7 is the same as permanganate. Yeah? So you either say manganate 7 or you say permanganate. But most of you are used to permanganate, which is okay. So you need to know that reaction of potassium permanganate with alkenes is the same as that with alkynes. What do I mean? They yield the same what? The same products. So you can recall, what did I say about the reactions of the manganate with alkenes? Whatever I said is the same as for alkynes, in that the products are the same. If maybe you want me to say something, I don't want you to call me a bad person. those products that are formed when alkenes and alkynes react with that potassium manganate 7, they are called carboxylic acids with single L. Those same products are what? Carboxylic acids. And I talked of carboxylic acids in the beginning. But don't worry, we have lessons on carboxylic acids, like carboxylic acids are alone. So all those things will later come back, but at least have a sense of direction. What you need to know, that one is a reagent. It is just a reagent, but I told you in these things of chemistry, organic, there is what they call reagents, and reagents cannot work alone. They always need what? Conditions. So in your research, I want you to be a good student. You find out what are those two conditions. What are those two conditions? So this is some sort of a note, but it has some assignment within. And I will tag it as assignment. So this assignment is top notch, because without it you may not find peace in further topics. You find out. I've tried to guide you. You have the best guidance as far as those assignments are concerned. So you take this screenshot. I don't know which one you last took. You people, where did we stop? Ah. Which is the last screenshot we took? Which one? I can't recall. Okay, very fast. You take that. You be fast. Then take that very fast. You be fast. After that, you take that one too very fast. Be fast, be fast, be fast. After that, that one where you have duplicated research work and the write-up dummy for that assignment. And these are easy things. And I remember telling you, whatever is outside the research work, you may need it in the future, but as far as the topic is concerned, you may not need it. That's why you see most of the things are later. But when you have all this, at least you know that now I have the whole thing in my farm. Okay. You also take that for the substitution reactions where we have the directions. Then as you people take that, you tell me whether that page is okay. I've said a lot on this page. You just say, you comment in the chat that page is okay, page is okay, page is okay. That's what I want to see. So that I tell you the last thing. We are supposed to end this lesson in the next 1 minute. We are done. But I want to give you the last guidelines. Just say page is okay because a lot has been said there. Okay. Yeah, that is the assignment. Yeah? Identifying triple bond, go to the same location. Now, this is the last thing. This is the last thing. Yeah? Combustion of alkynes. In combustion of alkynes, I'm going to ask you to revisit those people who copy my notes. You are the safest. Revisit combustion. Revisit combustion of alkenes and write the equations of combustion, the equation of combustion of alkynes in formats. Those who recall, we had two formats. Which were those formats? The first format was the format of CXHY. You see? Then the other format was the format of CN H2N minus. Remember, in lesson 1, we agreed that is the general formula of alkynes. And I remember teaching you how you can transfer the equation from this format to this format. Hey, so the combustion of alkynes is still like an assignment. You see why I want people to have a lot of assignments? They will keep you busy. They will keep you busy and in line with your academics. Then how will you fail to make it academically? We just have discussion groups and win with the team. Yeah, you cannot win as an individual unless you're extreme. So that is it. It will be very easy. Even in that lesson of alkenes, I talked of alkenes and alkynes. That's why I'm sending you there. But trust me, if you have a discussion group with someone who knows that of alkenes, there and then they just take you through that of alkynes. You save time. Other than you going back to revisit a video of 4 hours. Unless you're just a student who is lucky in that you can go to that video, you skip until you reach combustion of alkenes, then you listen for those 20 minutes and make notes. You have all the resources. Don't even complain. So now go to the syllabus book. Identifying is also done. I've talked about most things. Yeah. So lastly, as you people go, lastly, yes, before you people get less than 20, lastly, we are using just 15 seconds for this. So you be patient. Be patient. When we get ethane, you listen. When we get this ethane and heat it at temperatures of between 60 to 70 degrees Celsius, in the presence of a catalyst they call organonickel catalyst, who can tell me in the chat what we get? I've said, when you get this ethane, that one is ethane, and you heat this ethane at those temperatures, anything within that range. Of course, this one is better because we shall not have any excuse, like the temperatures are not enough. That one is better. When you heat it at those temperatures, in the presence of a catalyst they call organonickel. If they don't call it organonickel catalyst, they will call it complex organonickel catalyst. You get it? I'm putting complex in brackets to show you that with or without the word complex, your work is still fine. Who can tell us what they get? You people, no one knows what we get. Hey, at least you're going to learn that. Take a screenshot, put on your status. You people fear posting work on your status because you're like, hey, these people will judge me. They'll be like, I'm posting chemistry, yet I got F. You people, yes, we are studying, but we are just going through the process. But life is not about the F of chemistry. Life is not about the A of chemistry. In the end, life will be about the grace of God. Yes, even with a lot of content, if you don't have the grace of Allah, if you don't have the mercy of God, you're gone. I've said, ethane, heat it at that temperature range. 70 is better because we cannot have excuses like, let's increase the temperatures, blah, blah. We are doing this in presence of a catalyst. You know what catalysts do? And the catalyst is called organonickel. Between organo and nickel, there is the hyphen. Because nickel is inorganic, according to the periodic table. So organo, to show that there are some organic compounds. Why the word complex? It is a complex. Why? It is composing of nickel, which is inorganic, and some other organic things. That's why it's organonickel. But those are all stories. So what really happens is this. What really happens is this. We get the benzene ring. We get the benzene ring. We get the benzene ring. That's my favorite reaction in chemistry. That is my favorite reaction in organic chemistry. Why is it my favorite? Ethane is a straight chain, but you do something and straight away you get the benzene ring. The benzene ring is my best structure in chemistry. So anything that relates to the benzene ring is a turn on. It is a green flag academically. So what has happened is what they call polymerization. So I'll put there a note and say ethane is what? Polymerized. Someone can use that word. It is also okay. Because why I wanted to end with this, I'm going to tell you why. Ethane is polymerized. I want someone who has understood the ethane, that we are heating it at that temperature range, and which temperature is better, the name of the catalyst, what we are forming, and what is actually happening to ethane in the name of it being polymerized. Who has gotten all that? I have a question for you. And you never know, I may give you free classes, or a discount, or a present. This is called benzene, or someone can call it the benzene ring. Who has gotten all the chemistry surrounding this thing? Like when for you you're there and you feel like whatever is on the screen, I know. Who is that person? Who is that person? Who is that person? Who is that person? You people, no one. You people. You people. No one is okay with all that. No one can raise up their hand. Why are you giving people's names? Why not you? You also text your one name. You say scholar. Why are you texting your friends' names? So you people, A pressure among conditions, a pressure of 5 atmospheres may or may not be included. Yeah? May or may not be included. So if you come across a book with the 5 atmospheres in addition to those temperatures, it is okay. If you don't find another book without them, it is okay. So you people, I don't know. No one is okay with what is on the screen, even when you're seeing it. Now you people are just annoying me towards the end of the lesson, and I don't like that. We are hitting ethane at 60 to 70. But 70 is better because we shall not have any excuses. After all, there is no better temperature. We are heating it in presence of a catalyst called organonickel catalyst. We can add on the word complex. Why complex? You're mixing nickel, which is inorganic, with some other organic compounds, so they are complex things. What are we getting? Benzene. Or someone can say the benzene ring. How does it look like? Like that. And someone can say in short words that ethene has been polymerized. You know, polymerizing means you're making copies of something, eh? And you can see ethane is just something small with just 2 carbons. But then the benzene ring is having 6 carbon atoms. So there have been some polymerization that has happened. You get it? Benzene ring 6 carbons, ethane 2 carbons. So 3 copies of ethane have been made. And that is the polymerization we are meaning. But those are stories. So, and I've said a pressure of 5 atmospheres may or may not be said. So, anyone who is okay with what I've said? Anyone okay with what I've said? Let me do my role. Let me do my role. Thank you for making me look stupid. Thank you for making me look stupid. So reagent replacement, if you're having your ethane, so this is the old part, like the alternative, and you really want it to go to the benzene ring, we can have some 2 pathways. Yes, you either use solid copper or you use iron solid. Copper will work at 400, iron will work at 600. Yeah, copper at 400, iron at 600. That's alternative, yeah? But the best reagent is the other one of complex, organonickel. That one is the best. But these are replacements. Copper at 400, iron at. Why I decided to end with this? Because, anyway, you all know that the different applications are your research work. Eh? The applications of alkynes, of course, in real life, not any other life, they are your research work. Now, why I ended with how the benzene ring can be worked with or can be generated is because our next stop or the next topic, can say next stop or next topic, the topic is called benzene and methylbenzene. That is the next topic. So that is the next topic. So the timetable is having alkyl halides. That is on Saturday night. But that Saturday night, which I called the coverage night, shall be for benzene and methylbenzene. And we shall, I don't know if we shall complete, but I'll try my best. If you people comply, I'll try my best. I may split it into two, no need of panicking. I may cover it and complete. So I think you've realized why I really want to end, why I ended with how ethane, an alkyne, can give you the benzene ring, because it is the next topic. So that's where we shall begin from. So I'll sign out. So I think today let me sign out with my real signature. Signing out as Paul Tutor, tutor of chemistry and math at CMOS. Those who want to get more of our material, visit our website, chemmathonline.com. Reaching out to me is only this via WhatsApp call. If I don't pick, you leave a message. Otherwise, thank you for attending. The syllabus, different applications out. These ones have been talked about, even polymerization. Yeah. So let me tell you the last good news. So when I finish methylbenzene and alkyl halides, we shall be done with the organic chemistry of let me show you something here. You look at my screen. When I finish, let me show you here, senior 5 term 3 work. I think this is senior 5 term 2. Organic chemistry 1, you're supposed to cover the introduction. We got done. Alkenes, we got done. Alkenes, we got done. Alkynes, we got done. That was for term 2. Now, when I go to term 3, there is part 2 for organic chemistry 1. And in part 2, we have halogen compounds, or the alkyl halides, then benzene and methylbenzene. So for me, I'm going to begin with benzene, then later, halogen compounds will come. Now, when I get done with these two, the whole of organic chemistry will be done. The whole of it in the syllabus book. Why? These two mark the end of organic chemistry 1. The other organic chemistry is in senior 6. So when I come here under the senior 6 folder for the new curriculum, I think in term 1, you're supposed to do organic chemistry 2, which is topic 9. I don't know if people are seeing my screen. So that topic 9 has 2 things. Topic 9, sorry. It has 3. It has alcohols and phenols, carbonyl compounds, then carboxylic acids and their derivatives. So under alcohols and phenols, I have that review lesson. All alcohols were covered. So those ones were done. Then I have carbonyl compounds, where we have 3 lessons and everything was covered. Then in carboxylic acids and their derivatives, we have there 2 lessons. One lesson for carboxylic acids completed, another one for the esters, which are the derivatives, also completed. That means for senior 6 term 1 organic chemistry 2, you are done. Now you do organic chemistry again in term 3, because you can see term 2 you don't have any organic chemistry. It is only electrochemistry and periodicity 2, which periodicity 2 I showed you that those videos are already there. So when I go to senior 6 term 3, this is where I'm going to find organic chemistry 3. And here I studied 2 things, amines and polymerization. Amines, the lesson is there already. The only thing that we've not covered is polymers and polymerization. And we shall cover it next holiday. And I'll be done. So organic chemistry, when we finish benzene and alkyl halides, we shall only have polymers for next holiday. Otherwise, it will be 95% done. that is it. Yeah, that is it. Otherwise, thank you for attending. Yes, thank you for attending. Think we shall meet when we are supposed to. The timetable is clear. Review the work you're supposed to review. The drive has a lot of things you've not yet covered, yet you're supposed to go to school very soon and prepare for school. So use the drive and exhaust it. Those in day, you will access it throughout the term. No pressure. And we shall cover more topics during term 3, so that those people who come in holiday will find them there. Something like that. Yes. Otherwise, bye-bye. We thank God for the session, and we pray that He sees us through next time we meet. Amen.